So the next time will be about 3D vision, depth estimation, depth completion, and 3D detection. It will be given by Anton Konushin, acting head of Samsung AI Center in Moscow, and also a professor of Lomonosov Moscow State University. Anton, the floor is yours. And my name is Anton Konushin, and I'm head of Research Center of AI by Samsung in Moscow, and we'll talk about the tasks of 3D computer vision and some interesting ideas that developers of our center have put forward. 3D computer vision belongs to the area of spatial artificial intelligence, and spatial AI is the basis of all robotics. That what helps robots be oriented in the environment, plan their interaction and interact. And spatial AI is an important part in 3D vision. And three main tasks of computer vision is depth sensing and recognizing objects in 3D space. Depth sensing is the estimation of the distance from the camera to each point in the scene. And there are two main options of posing this task. The first one is sensing the depth just by the image. For example, single view depth estimation. We have an RGB image and we have to use it to estimate the depth map. The other option is depth sensors maps. So there is a task to complete the depth when we need to restore the missed values and mitigate the errors in the center. 3D object detection can be seen as a generalizing of tasks of 2D detection. So in 3D detection, it is not enough for us to detect where the objects are located in the environment. We need to also determine their geometric coordinates within, for example, a restricted rectangular. For example, here you can see the 3D detection of cars. So I'll start of depth map assessment with the first approaches. The boom of its development started when modern deep neural networks appeared. The general idea is as follows. There is an image in the input, and in the output there is the depth map. To train these kinds of models, we need a data set that is composed of pairs. RGB image and sample or control depth map. And we have to use images with segmentation of images. But there are not many data sets of this kind, and gathering these kinds of data sets require 3D sensors, special devices. So an interesting alternative idea that enables to gather much more data than we can do with 3D sensors is training depth estimation on stereo data. For example, we consider a task of disparity estimation of image, and we have left and right image, and we predict the inverse depth, the same as disparity for the left image, and we use this inverse depth or disparity to adjust the right image, and then we compare the converged right image with the disparity image, and the depth should be the same. And on the error, we estimate the depth quality. In stereo data, for example, all the 3D cinemas are stereo data, so we can use a lot of them. There are the following problems. Depending on what data sets we use, the depth data that are accessible to us are different. The absolute depth, that is the distance in meters from the camera to the point of observation, is important, and these are the data that we receive when we use 3D center. But if we reconstruct the scene with the help of stereo, either binocular or other series, we do not have absolute depth. The data have the accuracy to certain shift, and that is a problem because the distance is not metric, but with the accuracy of unknown parameters. And UTS, or up to scale distance, is such that the neural network shows the distance in virtue of depth that is known to us with this accuracy of coefficient. And when we have passive stereo, and then the result is disparity, and the true value of depth depends on the disparity with the accuracy to unknown scale and unknown shift. If the shift is known, then 3D reconstruction of this depth map is incorrect because the scene is distorted, the angles are distorted. Therefore, the data that we receive are impossible to be used in the analysis.
We offered a nice idea in one of our types, so we can train our models on a mix of data sets, counting a number of them. For those where we know the true depth, we will calculate it as a loss function for UTS, and also for methods where the scale is known. The passive stereo, where the scale is unknown, we'll only use the components destined for those scales. Altogether, we can train a model on data sets, on all data sets available, but on the other side, we evaluate geometrically correct models with right angles. So if you can see on this slide the visual comparison, so geometrically the model is gives a result which is true geometrically being right, and it's free. You don't need any extra computation resource. Now, the depth completion. One of the tasks is that now we use depth sensors with a very different approach to depth evaluation. There are sensors like Microsoft Kinect that build depth maps, and you have information, semi-depth map, where you have information for some areas. There are like sparse depth measurement as well. So in most methods, that type of maps is used, and this is quite popular with academic communities because data set Katie uses that data. But even on these images, you see that the nature of data is very different. So as the nature is different, the algorithm to achieve the best results for a depth map also should be structured differently. But those opportunities are not fully used by the researcher. The main problem is how do you merge that diverse information from image and from the depth map. Actually, there are depth assessment methods or use an additional information like surface normals and boundaries, and then this information is used from the sensor depth to get the final result. The other result is building a neural network where you merge information from depth maps and real images inside. So you supply two different decoder branches, you build pyramids of attributes, and unite attributes from the depth decoder and depth maps and generate the final depth. The methods are quite complex, and the main difficulty is how to use the difference from the attributes. A number of years ago, there is an add-in and space blocks, a method for how you build a depth map. So it is actually a generation of depth map by images and all attributes given some guiding features for the spade block and other blocks. But what could be that guiding information? If you use sensors with dense depth map, it can be taken from the masks of whether there are pixels or if there are not. So you see monitors with and without depth, and we suggested that it should work differently. So we built a network with encoder and decoder, and then we would send the guidance signal based on what the mask showed. So this method was efficient for generating depth map. You see the sharp edges, and also you can assess the density of for generation images. Another goal is like 3D detection. It's very close to 3D reconstruction task as such. One of the most interesting approaches to how you do it with a neural network, you take separate images, you compare the attributes like in 2D network, then you project them to the volume, and then you generate the marking. So we tried to use it for video to predict boundary boxes, 3 boundary boxes. We used in-voxel net. You take the image, you take out distributes with the 2D network, you project them to 3D volume, and then you launch a 3D network that would predict the boundaries. And experiments shown that this model allows to build a neural net quickly, because it takes its monoculum, but it gives state-of-the-art result for all data sets. And you can use it for single frames or different frames, multi-view. When you unite attributes, you can use it for video, where accumulation is sequential, and you need to know what voxels should be used. If there is no information, then we will add it to all attributes. Given images we got from the pixels. So all results are published, and source codes are available at GitHub of our center. I think I should stop here. Thanks for your attention. If you are ready, I can answer your questions. Anton, thanks so much